Let's start by reminding ourselves the parts of a right triangle. Now a right triangle has a 90-degree angle. And of course it can only have one 90-degree angle because you can only have 180 degrees in a triangle. So once you've already used 90 degrees, you can't use it again because that means the third angle has to be 0. If two angles are 90 or more, you've already run out of degrees. So we use this symbol right here to represent a right angle, and usually they won't write 90 degrees inside of it. Now this is a leg right here, mark it with a line, and this is a leg right here. How do I know that? The two legs are the two sides that are adjacent to the 90-degree angle. In other words, I know this is a leg and this is a leg because the point where they meet, the vertex, is at the 90-degree angle. So legs have their vertex meet at the 90-degree angle. You see this leg right here and this side, they meet up here not at the 90-degree angle, so I know that they're not the two legs. I know these are. So this is leg and this is a leg. We usually refer to one leg as leg A and the other leg as leg B. You could switch the order. This other side we usually call C, and that equals the hypotenuse. This seems like a long and cumbersome word, but it relates to the Egyptian word for rope. Measuring right triangles helps us measure the area of land, and they use this tool, the rope, to help measure and connect the sides. How do I know it's a hypotenuse? Well, it's the only side left, first of all, but also I think of it as being the side that's across from the 90-degree angle. So here's the 90-degree angle, and if I draw an arrow that goes up to this side, I have the hypotenuse. Those are the parts of the right triangle. Now the Pythagorean theorem is quite an interesting theorem, and we're only going to touch upon it right here. But it says that this side, whatever it is, we'll call it A in this case, here's the right angle, and this side have a very important relationship to the hypotenuse, which is this: that if you take side A and you multiply it by itself and you add it to side B and multiply that by itself, what you always get is exactly C times C. An abbreviated way of writing this is A to the second power, or A squared, plus B to the second power, or B squared, always is the exact same value as C squared. Now you might see that to be not important, however, it doesn't work for any other type of power. For example, A to the third plus B to the third never equals C to the third. In fact, there's no other power where this works. It only works for the second power. So now we have this relationship where A and B and C are related, where A squared plus B squared equals C squared. In simpler terms, let's say A was 3 and B was 4 and C is 5. Let's put these numbers into the Pythagorean theorem and see if it works. A to the second power plus B to the second power. Well, A to the second power is 3 times 3, or 9, plus B to the second power is 4 times 4, or 16, which is 25. Now, if we're correct, that should also equal C to the second power. C is 5. So C to the second power equals 25. And there we have it, that A squared plus B squared equals C squared. Why does this work? Many ways of looking at it. Let's look at a few. So here is a little program that shows us how the Pythagorean theorem works. It doesn't matter how big or small the triangle. It could be any way. It could be short, it could be really tall, it could be really skinny, or really fat. Either way, it doesn't matter. A squared plus B squared equals C squared. And look at the bottom here. If a was 10 and b was 10, well, then a squared is 100 and b squared is 100, and c squared would have to be 14.14, which is also 200 when you square it. Doesn't matter how I arrange this shape, I always get equal sides when I square a over here, and b over here. That equals c squared. But it still doesn't show us why. It's an interesting way of looking at it. When we say that a to the second power plus b to the second power equals c to the second power, we're talking about squares. Remember, a squared, let's say this is a squared down here, means a times a. And remember, that's how you find the area of a square. So here's a squared, or a to the second power. Here's b squared, which is actually a square. And here's c squared. Let's see what happens when we move this stuff around. Is it true that this red square and this green square are exactly the same size when we add them together as this blue square right here? And we can mess around with it. Okay, I'm moving it. Now let's try to move this and see what happens. Watch this square move right here. We're not changing the size of it, we're just bending it and moving it so it fits right into there. Do that again. So a squared, when we move that square and just mess around with the shape a little bit, we can get it to fit like that. The overall area hasn't changed, we just moved it. Now, watch b squared, the green square. We're not changing its shape and size, we're just moving it into c squared. I'll do that again. B squared, move it around, fits right into the c square. So we moved these two squares, we added them up, moved them over here, and we got c squared. Now, that's exactly what our equation is saying. A squared plus b squared equals c squared. And we can use this to solve for all kinds of stuff. In this situation right here, let's start by labeling our parts. This is the right angle. The two legs have their vertex and meet at the right angle. So this could be A and B. And here's our hypotenuse. So our formula is a squared plus b squared equals c squared. A is 5, so a squared is 25. B is 7, so b squared is 7 times 7, or 49. Add these up and we should get c squared. Let's try it. 25 plus 49, that is 40 plus 20 is 60, plus 5, 65, plus 9, 74. So c squared is 74. This means to find c, we take the square root of 74, and that's our answer. C equals the square root of 74. This side right here, again, we have a right angle, our legs, and our hypotenuse. So this time, 3 squared plus b squared, we don't know what it is, has to equal 5 squared. So simplify this a little bit. That's 9. We still don't know our mystery number. And 5 squared is 25. Let's use our understanding of algebra and inverse operations here. If 9 plus something squared is 25, then 25 minus 9 equals that something squared. So something squared equals 25 minus 9, or 16. And that's something squared. Well, what number is square root of 16? The answer is 4. And in fact, when I saw this triangle, I knew right away the answer was 4. How did I know that? There's something called the Pythagorean triplets. And it's kind of a misnomer because we believe that people before Pythagoras, the Babylonians for example, we believe they recognized the triplets long before he did. But we call them this anyway. Here's an example where 3 squared, these 9 squares, plus 4 squared equals the 25 squared. So our first triple is actually a 3, 4, 5 triangle. And our next triple, notice all we did, instead of 3, 4, and 5, we doubled everything. So 3 is 6, 4 is 8, and 5 became 10, and the relationship still holds. We can keep going. Now we have a unique triplet. It's 5, 12, and 13. It's different from the other. there are many different unique triplets. 9, 12, and 15. 8, 15, and 17. 12, 16, and 20, and so forth. We can mess around with these. There's all different kinds. However, we should realize that the reason they're called triplets and they're so special is because each of the numbers are whole numbers. If we go back to our example from before, see this, how we got c equals the square root of 74? That's an irrational answer. The Pythagorean triplets are nice because they always give us a rational answer. For example, if I had a right triangle, here's a rough sketch, and it was 3, 4, blank. Now that we know the triplet, we know it has to be a 5, but let's figure it out. A squared plus b squared equals c squared. A is 3, so a squared is 9, b is 4, so b squared is 4 times 4 is 16. This equals c squared. 9 plus 16 is 25. So 25 is c squared, and in fact, many multiple choice questions will offer this answer right here, 25. Students rush and often pick it. However, we don't want to know what c squared is. We want to know what is c, this length, not the square of it. So the way we find that out is by taking the square root of 25. And that's 5. Because 5 times 5 is 25, so c equals 5. What's also interesting to note is that sometimes if a squared plus b squared doesn't equal c squared, you don't have a right triangle. So here's our symbol for does not equal. So let's say we had a 4, a 5, and a 6. Is this a right triangle? Well, you could measure it and test if this is a right angle. Or we can use the Pythagorean theorem. A squared plus b squared, if this is a right triangle, it will be exactly the same thing as 6 squared. Well, 6 squared is 36. 4 squared is 16, and 5 squared is 25. However, what is 16 plus 25? It's 41. 41 and 36 are not equal. So a squared plus b squared does not equal c squared. Therefore, it's not a right triangle.